So we've seen now how to do double integrals when we're using rectangular coordinates. What we want to do here is we're going to set these up with polar coordinates. So first let's just review polar coordinates a bit. So recall that normally when we're looking at a point in the xy plane, we say its x direction and its y direction, and that uniquely determines a point. We can also uniquely determine it with polar coordinates. So the polar coordinates are r, which is our distance from the origin, and then theta, which is the angle from the positive x-axis. So here's an illustration of this. If I have the point x0, y0 here, I can tell where it is by saying I go x0 units in the x direction, y0 units in the y direction, and that gets me here. But I could also say, well, take this angle theta, travel along the ray out a distance of r, and that will give me my value as well and gets us the exact same point. So notice from our relations here, the x coordinate, we can think of this as a triangle, forming a triangle here. So the x value here is related by r cosine theta, the y is r sine theta, and then we also have with the triangle r squared is equal to x squared plus y squared. I didn't put the subscript zeros here even though they go with the picture just because we're used to seeing it more without the subscripts there. So we'll make use of these relations quite often. So it is important to remember them, but you can just get them from the triangle as well. So just to get an idea of what the graphs look like, if we fix a value of r, we just obtain a circle centered at the origin. So for instance, if I look at all the points where r is equal to 1, that gives me a graph like this. What this basically means is that if we're working with circles, it's going to be simpler to work in polar coordinates than it is to work in rectangular coordinates. And similarly, if we fix a value of theta, then we just obtain a ray originating at the origin. So here we see the blue line here is when theta is equal to pi over 4. So again, if we want to work with rays originating at the origin, then polar coordinates are much nicer to work with than rectangular coordinates. So the whole reason we're looking at this is there are situations that arise when polar coordinates is much nicer to use than rectangular coordinates when doing calculus. So for instance, suppose I have an integral where I want to integrate f of xy, so a function of two variables, over some region r in the xy plane, and suppose this region looks like this. So we have here a circle of radius 1, a circle of radius 2. This is the line y equals x here. This is the line y equals minus x. And we want this region r inside of this. Now, if we wanted to set this up with x and y limits, this would be an absolute nightmare. Because we'd have to, if we wanted to do, say, fix a y, we'd have certain value, we'd enter along this circle and x along the circle from here up to here, and then we'd enter on this line and x on the circle, enter on the line and x on the circle. And we get all kinds of integrals with square roots of 1 minus x squared, 2 minus x squared, things like this. And so those are not really nice to work with. So we can see, though, that the limits on this region, on this part here, are circles, and this part, they're rays. So this tells us exactly that this is the situation where polar coordinates would work quite well, because polar coordinates work well with circles and rays. So this is what we just went through. It's not going to be pleasant to set those limits up. So we'd like to do this with polar coordinates. Now, in the case of rectangular coordinates, when we were setting up our definite integrals, remember we had our dA there, our little incremental area, was either dx dy or dy dx. And the reason for that was if we took delta A, so some fixed amount, small amount of area, we could write that as delta x delta y or delta y delta x. So just think of here's a little rectangle, and so it's just the width times the height. So the delta A is exactly delta x delta y. Now if we want to do polar coordinates, we need to figure out how to represent delta A and approximate that with a little change in r and a little change in theta. So the first thing we're going to do to kind of build up to this, it's not quite as obvious as what it is for rectangular coordinates, is we're going to recall the fact from geometry about the arc length on a circle. So suppose I have I have a circle out here. It's out at radius r, and we just take a part of the circle that corresponds to a little change or a little angle here, theta. So this arc length here, this length here is angle theta, and then we're out here at r, and we might ask, what is the length of this arc here on the circle? So maybe we recall from geometry, maybe we don't, but we'll need to use the formula that this is just r times theta. So for a distance r out, and we go a span of theta, the arc length there is r times theta. And you can think of this, if you think of just the whole circle, that would be the circumference of the circle, and so the angle would be 2 pi because we go all the way around, and we know the circumference of the circle is 2 pi r, so at least it fits in that case we're already aware of. So we're going to use this fact to approximate our delta A with delta r and delta theta. So here's the picture. Looks a little complicated. So we want to think of this part in blue here as this is some small amount of area. So this is our little delta A. I've drawn it bigger so that it isn't particularly small in the picture, mainly so we can see it. But you want to think of this as a tiny little piece of area. And so think of this as being r units out from the origin, and we have an angle of theta to get to here. And now what we're doing is we're taking a little bit of change in r, so we're lengthening our radius just a little bit, and we're extending our theta by just a little bit with a little delta theta. So what we just saw then is that this arc length here, this is the distance away from the origin, which is r, times the angle, which is delta theta. So this little arc length here is r delta theta. And then this length here is delta r. So even though this doesn't look anything like a rectangle here, remember we want to think of these values as very small. So you can think of, if this little area was very small, we could approximate it with a rectangle that had one side r delta theta and one side delta r. And then we could say our delta A is approximately r delta theta, one side of the rectangle, times delta r, the other side of the rectangle. And this approximation will get better and better the smaller delta theta and the smaller delta r actually are. So in the limit, we obtain that dA is r dr d theta. So notice it's not just dr d theta, where before we had just dx dy. Here we have to include that r because the little, how far away from the origin it is going to change that little piece of area. So now that we have the dA, we can go ahead and set up our double integrals in terms of polar coordinates. So let's look back at that integral that we were looking at when we decided we might actually want to use polar coordinates for integration. So we want to take that integral and we want to write it in the following form. And I know this looks very complicated at first, but just notice we're taking the dA and we'll write it in terms of r dr d theta. We're almost always going to use dr and then d theta. And then we're replacing the x and the y so that we have our function is turned into a function with just polar coordinates in it. And then our first limit, since our first integrand here is r, these are r equals g1 of theta and r equals g2 of theta. So often these will just be constants, but it is possible for them to depend upon theta. And then the outer limits are just our values of theta. So these are just some numbers. We can't have functions on the outside because we need to end up with a number at the end. So let's go ahead and look at our region again and see what our limits of integration would be in this case. So here's our region we were looking at before. And so now what we want to think of is, since theta is our outer limit, we want to think of fixing a value of theta and seeing what the values of r would be. Well, if I fix some value of theta and I take this dashed line here, where does it enter the region? It enters the region here when it hits this circle of r equals 1, and it exits when it hits the region when r is equal to 2. So my r limits for my integral are going to be from 1 to 2. And we can also see the smallest value, where do we start hitting the region in terms of theta, is down here at minus pi over 4. And then we'll trace the theta all the way up until we get here to pi over 4. So my theta limits are going to be minus pi over 4 to pi over 4. So this integral becomes quite nice in terms of the limits, whereas we would have had all kinds of square roots of functions when we were doing rectangular. Here we just have a limit from 1 to 2, and from minus pi over 4 to pi over 4. So of course, how easy this integral will be to do would depend upon our function and how that turned out with the r cosine theta and r sine theta, but certainly the limits are much easier in this situation. So we'll see a lot of examples in class of how this can be useful for various shapes and various functions.